Good evening, students. Welcome back to Yupp Master, the school foundation program. So, in the previous class, we are discussing about the isomerism concept. Some of the students are facing a problem in naming the alkanes, that is branched chain alkanes. So, and they have requested to give us the names from isomerism concept. Of course, as the number of carbon atoms in a alkane increases, the number of chain isomers that are possible are also increasing. So, the different chain isomers that we are going to write for a given formula and their IUPAC names, and the most of the cases in order to reduce the space, the organic compound is written in a short form or the zigzag fashion. So, the zigzag fashion of representation also some people are facing problem. So, as they have requested, today I am going to discuss the different chain isomers possible for C4, 4 carbon chain as well as 5 carbon atom containing alkane, 6 carbon containing alkane and 7 carbon containing alkane, and how we are going to name the organic compounds, the chain isomers of the alkanes. All these things we are going to discuss today. Okay. So, in the last class we have defined the isomerism. What is isomerism? Isomerism, it is the phenomenon of existence of two or more compounds having same chemical formula, but they are going to exhibit different physical and chemical properties. In the case of isomerism, we have seen the two different types of isomerisms. The first one is structural isomerism. Okay, structural isomerism. So, here the phenomenon of existence of two or more compounds having the same chemical formula, but the structural arrangement will be different, and that phenomenon is called as isomerism, and the compounds which are exhibiting this isomerism are called as structural isomers. Okay. And the other side, if you observe, we can categorize this isomerism as stereoisomerism. In the last class I have given you the concept of stereo. Stereo means it is a arrangement of the atoms in a 3-dimensional space around the central atom. So, stereoisomerism is with respect to the arrangement of the atoms around the central atom in 3-dimensional space available to it. Okay. So, it is a phenomenon of existence of two or more compounds having the same chemical formula, same chemical connectivity, same bond connectivity, but only the difference is the differential arrangement of the atoms within the 3-dimensional space are available around the central atom, and thereby we get a stereoisomerism, and those compounds are said to be stereoisomers. When you observe the structural isomerism, in the case of structural isomerism, we have seen or we have gone through so many different types of structural isomerisms: chain isomerism, positional isomerism, functional group isomerism, metamerism, tautomerism, and even we have seen the ring chain isomerism. So, when you observe the chain isomerism or positional isomerism or the functional group isomerism, whether it is a metamerism or the ring chain isomerism, the arrangement of atom within the structure, there is a difference in the structure of the compound, but the compounds will have same chemical formula, and thereby we get structural isomers. Okay. And in the case of stereoisomerism, we have seen the geometrical isomerism as well as the optical isomerism. So, geometrical isomerism and optical isomerism will fall under the stereoisomerism. And when you observe the geometrical isomerism is due to the restricted rotation of the carbon-carbon bond or carbon-nitrogen bond or nitrogen-nitrogen bond. So, when there is no rotation possible, generally we say that whenever the carbon atoms are connected with a single bond, so the bond can be easily rotated. So, the rotation can be easily assumed by taking two tomatoes, connect the tomatoes with one stick and try to rotate the tomato. Tomato will easily rotate, two tomatoes will rotate because they are connected with only one stick or one single bond. Here tomatoes corresponds to carbons and the stick corresponds to the covalent bond. Take two sticks of same length, and one side you take one tomato, attach one tomato, other side also you take one more tomato. Okay. Now try to rotate the tomatoes. It is not possible to rotate the tomatoes. because here the two tomatoes are connected by two sticks, two bonds. So whenever the double bond or a triple bond is present between the carbon atoms, so the rotation between the two that carbon atoms will be restricted. So the rotation is not possible in that case. So when the rotation is not possible, then in that case we are going to expect the geometrical isomerism. So here if the similar groups are present on the same side of the double bond, we take it as a cis isomer. If the similar groups or atoms present on the opposite side of the double bond, we take that configuration or that isomer as trans isomer. Whereas optical isomerism can be seen when we have a chiral center in the molecule, or asymmetric center presence is essential in order to observe the optical isomerism. So whenever the carbon atom is connected to 4 different groups, in that case we can expect the asymmetry. So the molecule which lacks symmetry elements is said to be asymmetric. Okay. So symmetry elements generally we come across plane of symmetry, axis of symmetry, etc. Okay. So when these elements of symmetry are absent in the molecule, we say that the molecule is lacking the symmetry elements, and therefore it is possessing an asymmetric center. Whenever a molecule has an asymmetric center, we can expect the optical isomerism, and the compounds that are exhibiting the optical isomerism generally taken as optical isomers. In that case, you can observe the D dextro compound as well as L levo compound. So dextro compound is that compound which can rotate the plane polarized light. So optical activity can be observed only with respect to the rotation of plane polarized light. So when a compound, when plane polarized light is passed through a compound, if the compound is capable of rotating the plane polarized toward the right side, it is called as dextro compound. If the compound is capable of rotating the plane polarized toward the left side, it is called as levo compound. So the compound which rotates the light toward the right side is dextro isomer, and the compound which rotates the plane polar light toward the left side is known as levo isomer. So dextro isomers and levo isomers are considered as optical isomers, and generally the non-superimposable mirror images are called as enantiomers in that case. Of course, when we look into the further functional groups of the organic compound, there we come across the different types of geometrical isomerism as well as optical isomerism. So as far as the alkanes is concerned, since we are dealing with the alkanes, the simplest hydrocarbons, and these are the mainly the parent chains for a generation of different functional groups in case of organic compounds. Okay, right. Alkanes, if you look at the isomerism, as we have discussed, alkanes will exhibit only the chain isomerism. Okay, since one student was asking us to why the alkanes cannot exhibit the positional isomerism or the functional isomerism. Since these are the parent chains, or the hydrocarbons contain only carbon and hydrogens, no other groups are present. Okay, so therefore alkanes are capable of exhibiting only the chain isomerism. So here we can change the arrangement of the carbon atoms within the alkane. We can change the arrangement of carbon atoms within the alkane, and thereby we can expect only the chains or the structural isomers, that too only the chain isomers. Okay, only chain isomers are possible. Again, when we can expect the chain isomers in the case of alkanes, when alkane contain only one carbon atom, when alkane contains two carbon atom, when alkane contain three carbon atom, these alkanes cannot exhibit chain isomerism. In that case, we can say that the carbon arrangement, we cannot arrange these carbons in a different fashion. So alkanes containing one carbon, two carbon, three carbons, the carbons cannot be arranged in a differently fashion or a different arrangement or different structural positions, and therefore we cannot expect the chain isomers in the case of alkanes. Okay, when we look at the isomerism, chain isomerism, from butane onwards, we can easily expect the chain isomers. So at least the number of carbon atoms that should present in alkane to exhibit chain isomerism is 4 number of carbon atoms. So 4 carbons means it is parent name is butane. So butane can exhibit the chain isomerism. So if we observe, we know the formula butane CN H2N plus 2 where N equal to 4. So it will be C4H10 is the formula. So let me first write the isomers in a expanded fashion, and then we will write in a zigzag fashion, and then we go for the naming of the compounds. Okay, right. So C4H10. So I can take 4 carbons in a straight chain Okay, and we know that carbon is a tetravalent. In order to satisfy the tetravalency, I am attaching the hydrogens CH3, CH2, CH2, CH3. Since we have 4 carbons, okay, so here the straight chain, only one chain is possible, there is no branching at all. So directly you can write the name of this particular compound according to IUPAC as butane. Butane is the IUPAC name. 4 carbon chain, and it is an alkane, all single bonds are present, so it is butane. Okay. According to the common naming system, we write it as N-butane. N means normal, so this is common name of this compound. Common name is N-butane. So if I go for representing the molecule with the zigzag arrangement or the zigzag fashion of representation, so in that case we write only the straight chains, I mean a straight line, so that the 2 terminals of this chain is having carbons, and of course here we are omitting the hydrogen atoms. It is to say that the corresponding number of hydrogens are present which satisfy the tetravalence of that particular carbon. So each turn or each corner will represent one carbon atom. So therefore we can write the molecule N-butane or normal butane or butane in this fashion. So CH3, CH2, CH2, CH3. So here this chain has 4 terminals, first one, second one, third one and fourth one. So since we are writing in this fashion, so it has 4 carbon atoms. It is to say that 4 carbon atoms. So this is the correct representation. This is the normal representation I am writing in expanded form, showing all the carbons and hydrogens. But when we want to omit the carbon and hydrogens, so directly we can write in a zigzag fashion. So this is 1 carbon, this corner is 1 carbon, this is 1 more carbon, and this is 1 more carbon atom. So we can represent the same molecule in this fashion. Just look at the number of turns that it has, 1, 2, 3, 4. So 4 carbons are present. So this is the butane. Okay, right. Let me take you or let me arrange the 3 carbons in straight chain. Okay, CH3, C, CH3. I am taking 1 carbon as a branch. So in order to satisfy the number of tetravalency of the carbon, I am giving the number of hydrogens to the molecule. Okay, so this is also correspond to the same formula C4H10. But what is the difference between these two? Here the 4 carbons are arranged in the straight chain. Here 3 carbons are arranged in the straight chain and 1 carbon is taken as a branch. Okay. So whenever we have a branched chains, according to IUPAC, whenever we want to name the alkane, branched alkane with IUPAC system, in that case we are supposed to select the longest continuous carbon chain. So I am taking the straight chain as a continuous carbon chain and I am numbering the chain as 1, 2, 3. Okay. Now at second position we have substitution. What is the substitution? The substitution is CH3, that is alkyl. So we write it as alkyl. Methane less than 1 hydrogen is removed, so it becomes CH3. It's called as methyl. Okay. So we have a substitution here. At second position I have substitution, so I am writing it as 2 hyphen methyl. Then we have 3 carbons in a straight chain, so it should be propane. So the parent name is propane. On propane chain, on 3 carbon chain, at second position we have methyl, 1 carbon chain, that is 2 methyl propane is the name of this particular compound according to IUPAC. Okay. When you look at the common naming system, in case of common names, what we have to do? We have to count the number of carbon atoms what we have. So total number of carbon atoms are 4. So whenever we have 4, the parent is butane according to common system. But how the 4 carbon atoms are arranged? Are they arranged in the normal fashion here? So I am writing it as normal. But whenever we have a methyl group attached to the second last carbon atom, we are going to use one prefix. What is that? Iso. Yes. So iso prefix we are going to use here. So we can write it as iso hyphen butane. Isobutane is the common name or common system nomenclature of this particular compound. So here if we observe, 4 carbons when we have, we can arrange the 4 carbons in a straight chain, or we can observe the 3 carbons in a straight chain and 1 carbon as a substituent as a on the second carbon atom of the straight chain. In this case, if I want to write this particular compound in a zigzag representation, so I will represent the 3 carbons in this fashion. I am representing the 3 carbons in the straight chain, okay, and I am attaching one at the second position. So this is the representation, zigzag representation of isobutane. So this is how we can represent the molecule. Still, is there any possibility to arrange the carbon atoms? We have arranged 4 carbons in a straight chain, 3 carbons in a chain, 1 as a substituent. We cannot arrange 2 carbons and 2 as a substituent, it is not possible. So we are going to get only 2 chain isomers. In this case, we are going to have 2 chain isomers for butane. So butane C4H10 exhibit chain isomerism, and it is going to exhibit 2 chain isomers. 2 chain isomers. Okay. Student, I think now you have got an idea how to write this molecule into the zigzag representation of the molecule, and how to identify the common name and the IUPAC nomenclature. Of course, it is a simple molecule, so it is easy to done. Let us look at a little complex compared with the butane. So pentane C5H12 is the formula. Now in this case, let me write the 5 carbons in a straight chain. Okay, right. Let us start writing CH3, CH2, 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 CH3. Students, always keep pen and paper with you, so that as the class goes on, if you write on the notes, then you can easily understand what is exactly going on. Okay. So here, if you observe, I have arranged all the 5 carbons in a straight chain. Okay. So if you look at the name of this compound, 5 carbon chain, we know according to IUPAC we can write it as pentane. Pentane is IUPAC name. Okay, right. According to the common name, since all carbons are arranged in a straight fashion, we write normal N. So we are going to use N prefix pentane. 5 carbons are present, so I am writing it as N pentane. So this is the common name of this molecule. How we are going to represent the 5 carbons? In a zigzag fashion. So let me take 1, 2, 3, 4, 5. So I am arranging 5 carbons in a zigzag fashion, 1, 2, 3, 4, 5. So it is exactly the same molecule pentane. Okay, right. Now let us look into the arrangement of 4 carbons in a straight chain and 1 carbon as a substituent. Okay, in that case, if I go the arrangement of 4 carbons in a chain, straight chain fashion, and 1 carbon I am taking it as a substituent, CH3, CH2, CH, downward H, CH3, and other side also CH3, right. Now according to IUPAC, if I want to name this compound, I have to select the continuous carbon chain. If I select the continuous carbon chain, the straight chain is the continuous carbon chain having maximum number of carbon atoms. So this is the selected chain. So when after selecting the chain, you have to write the number, we should give the numbering to the carbon atoms in the straight chain or the parent chain, such that we can name the substituents that are present at the different positions. Right, let me name or number this compound from left to right. So I am coming from that side because the substitution is present on this carbon atom. So the substituted carbon should get the lowest possible numbering. So it is getting the second position. So at second position, what we have? We have CH3. CH3 is a methyl. Okay. So I will write it as 2-methyl. So I am mentioning the position of this methyl. It is present on the second carbon atom. So what is the parent chain? Parent chain has how many number of carbon atoms? 4 carbons. So I am writing it as butane. 2-methyl butane is the name according to IUPAC. Then what could be the name according to the common system of nomenclature? Second last carbon atom has a methyl group and no other substituents are present. So we can write it as iso. But how many number of carbon atoms we have? We have 5 carbons. So it should be pentane. So the common name is isopentane. Isopentane is the common name of this particular compound, right. So, how to write this molecule in a zigzag fashion? So, 4 carbons are present in a straight chain, on second carbon we have 1 carbon atom. So, first write the 4 carbons in a straight chain, okay. Then connect 1 carbon at the second position. So, this is the representation of isopentane or 2-methyl butane. So, these two are the same molecules, 4 carbons in a straight chain, 1 carbon as a branch. So, it is easy to write the structures once you know the each corner will represent 1 carbon atom, and we are omitting the writing carbon atoms as well as hydrogen atom. It is understood that the tetravalency of the carbon is satisfied with the help of carbon or hydrogens, okay, right. So, can we arrange the 5 carbons in another fashion? Yes, it is possible. 5 carbons in a straight chain, I have taken 4 carbons in a straight chain. Let me take 3 carbons in a straight chain. So, when I take 3 carbons in a straight chain, 2 more carbons I have to accommodate. So, I am accommodating the 2 carbons on the central carbon of the 3 carbon chain, and I am selected this as a longest continuous carbon chain having 3 number of carbon atoms. So, straight chain I have taken. At second position I have methyls, and again when you observe this carbon accommodating 2 substituents, 2 methyls are present. So, in that case what we have to write? We have to write the name as 2 comma 2, since similar same substituent is present. So, I am writing it as dimethyl. How many carbons we have as a parent chain? 3 carbons. So, the name should be propane. So, 2 comma 2 dimethyl propane is the IUPAC name of this particular compound. It is an IUPAC name, okay, right. Now, I have a 5 carbon chain, I have 5 carbons in this molecule. So, it should be pentane, and when you observe the second last carbon atom has 2 methyls, in that case we are going to use a prefix known as neo, okay. So, we are going to use the prefix neo. How many carbons we have in the molecule? 5 carbons. So, it is pentane. Neopentane is the common name of this particular compound, okay. So, common name is neopentane, IUPAC name is 2 comma 2 dimethyl propane, right. So, how to represent this molecule? So, I want to represent this molecule in zigzag fashion. So, I can represent this molecule in a zigzag fashion as the simple plus symbol. What does it indicate? So, here the junction indicate 1 carbon and the terminals will indicate the 4 carbons. So, total 5 carbons are present, or I can write it as, I can also write this way. I will write the 3 carbon chain as a parent chain. So, I can attach the 2 methyls on this position. So, I can write in that fashion also. I can represent the molecule with a plus, or I can represent the molecule in this fashion, 3 carbons in a chain and 2 carbons as a substituent. So, this is how we can easily write the zigzag representation of the molecule, okay. And in the zigzag fashion of representation of the molecule, no need to represent or write the carbons and hydrogens. It is understood that the tetravalency is satisfied and number of hydrogens and number of carbons are present in the given connections or bonds, okay, right. Still, is there any possibility to arrange the 5 carbons in other way around? No. We have arranged 5 carbons in a straight chain, 4 carbons in a straight chain, 1 substituent, 3 carbons in a straight chain, 2 substituent, and it is not possible to arrange in a taking 2 carbons as the parent chain and arranging the other, okay. So, only 3 chain isomers are possible in the case of pentane. In the case of pentane, 3 isomers, chain isomers are possible, okay, right. As the number of carbons increases, the isomer number is increasing. Let us see one more alkane C6H14, 6 carbons and 14 hydrogens. So, in this case, let me write the compound CH3, CH2, 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 okay, then CH3. So, I am arranging all the 6 carbons in a straight chain, all the 6 carbons in a straight chain. So, I can represent the same molecule in a zigzag fashion, 1, 2, 3, 4, 5, 6. So we can write the molecule in zigzag fashion this way. Look at the corners 1, 2, 3, 4, 5, 6. 6 carbons arranged in a straight chain. Right. So the name, if you observe, it is hexane. So I will write only the IUPAC names now, so that you can accommodate all the isomers here. So this is hexane according to IUPAC nomenclature. N-hexane according to the common name of naming system, N-hexane. Okay. Right. Now I will take 5 carbons in a straight chain and 1 carbon as a substituent. Let me see how many different types or different fashions I can arrange these 5 carbons: CH3, CH, CH2, CH2, CH3. Okay. I have taken 5 carbons in a straight chain, 1 carbon as a substituent. Look at the total number of carbon atom, 6 only. Total number of hydrogen atom, 14. It is satisfying the formula. Okay. Now, if I go for the naming of this compound according to IUPAC system, so I can I have to select the longest continuous carbon chain, which is going to give us the parent name. So if I represent the molecule in a zigzag fashion, I am arranging the 5 carbons in a straight chain. Okay, 1, 2, 3, 4, 5. Okay, and 1 carbon I am taking it as a substituent. Right. Now I have to name the compound according to IUPAC. So in that case, I have to number the chain. So this is 1, this is 2, 3, 4, and 5. Okay. So at second position we have methyl. So I can write the name of this compound as 2-methyl. At second position I have the substituent, that is substituent is alkyl methyl group, and we have 5 carbons in a chain, so it is pentane. 2-methyl pentane is the name of the compound, IUPAC name of the compound. What is common naming system? At the second last carbon atom we have CH3 and no other substituents are present on the chain, so it is isohexane. Okay. Right. Now if I arrange, I have arranged the 5 carbons in a straight chain and I have taken methyl at second position. I also have one more possibility is there in this case. You can take 5 carbons in a straight chain, but we can take this substituent 1 carbon at the third position. So if I am going to write that one, CH3, CH2, CH, CH2, CH3. Okay. At third carbon, I am taking the 1 carbon atom as a substituent. Okay. So if I go for the numbering, it is 1, 2, 3, 4 and 5. So 5 carbons I have arranged in a straight chain fashion. The 1 carbon is taken as substituent, but when you compare this one and this one, here the substituent is present. The substitution carbon is taken at second position. Now we are taking the carbon at third position. So when you take the name of this compound according to IUPAC, it is 3-methyl pentane. 3-methyl pentane is the IUPAC name. So if I want to represent this molecule in a zigzag fashion, how to represent? So let me write the 5 carbons in a straight chain. Okay, I am writing the 5 carbons in a straight chain, and at third position I am taking the substituent, the carbon. So this is 3-methyl pentane. 3-methyl pentane. So when we have 5 carbons in a straight chain and 1 as a substituent, it is possible for us to arrange the substituent at 2 positions, at second carbon and at third carbon. If I want to substitute the 4th carbon, in that case I will start numbering from the other side. So that carbon gets the second position. So only 2 possibilities are there, at second position and at third position. So we are getting 2-methyl pentane, 3-methyl pentane. So these two are chain isomers of hexane. Okay. Still, is there any possibility to arrange the carbons? Yes, we can take only the 4 carbons in a straight chain and we can take 2 carbons as a substituents. In that case, how to arrange the carbon atoms? Let me take one more. So this is with respect to the number of 5 carbon chains. Okay. Now let us take the 4 carbon chain. CH3, CH, CH, CH3. Okay. Let me take a CH. Okay. Right. So let me arrange 1 carbon here. and one more carbon here. So, if you observe the total number of carbon atoms, 6 carbons are present. I am taking 4 carbons as a chain, 2 carbons as substituents. Okay, right. Now, after arranging the carbon atoms, we have to take the longest continuous carbon chain having maximum number of carbon atoms. So, straight chain I have selected as a longest continuous carbon chain having 4 number of carbon atoms. So, when you go for the numbering of this particular 4 carbon chain, so 1, 2, 3, 4, at second position we have substitution, at third position we have substitution. So, we can write it as, since the substituents if you observe both are methyls, so same substituent is present at second position and third position. So, just write the name of this compound by mentioning the positions of the substituent, that is at second position we have methyl, third position I have methyl. So, I am writing it as 2, 3, then followed by hyphen dimethyl. So, the 2 methyls, one methyl is present at second position, one methyl is present at third position, that is to say that, okay. And then what is the parent chain? It has 4 carbons, so it is butane, it is butane. So, we can represent this molecule in a zigzag fashion as, so arrange the 4 carbons in a straight chain, okay, take one carbon as a substituent, right, and then other carbon also as a substituent. So, this is how we can represent this molecule. So, I am writing 4 carbons in a straight chain, second position 1 methyl, third position I am writing 1 methyl group, okay. So, this is how we can arrange the 4 carbons and these 2 carbons as substituent. Is there any possibility to arrange one more fashion? Yes, we can arrange in one more fashion. How we can arrange? Let me write this way. CH3, I am taking 4 carbon chain as a parent chain, let us say. I am taking the 2 substituents on the same carbon atom. In the previous case, I have taken 4 carbons as a straight chain, one substituent present in second position, other substituent present in third position. Now, in this case, I am taking the 2 substituents on the same carbon. So, if you observe here, the continuous carbon chain will be the straight chain. So, this is 1, 2, 3, 4. So, at second position we have 2 methyls. So, in this case if I want to write the name of this compound, I will write it as 2, 2 dimethyl butane. 2, 2 dimethyl butane is the name of this compound. If I want to represent it in a zigzag fashion, how to write the zigzag representation? So, I can write the zigzag representation by taking 2 substituents on the same carbon. Taking 2 substituents on the same carbon atom, okay. So, this is how we can write the different chain isomers of hexane, okay. Is there any arrangement that is possible with the 3 carbon chain? No, we cannot arrange it, okay. So, how many total number of isomers are possible in this case? This is 1, 6 carbon chain. When you look at the 5 carbon chain, we have 2, so 1 plus 2, 3, and 4 carbon chain we have 2. So, 3 plus 2, 5. Total 5 chain isomers are possible for hexane. Hexane is giving us 5 different chain isomers. So, when we have alkane with the 6 carbons, so the 6 carbon atoms can be arranged in a different fashion. How many different fashions are possible? 5 different arrangements are possible, okay. It is very simple, just try to write down the carbon chain, decrease the length of the carbon chain and take other carbon as substituents, and then try to look at the positions and name these compounds according to IUPAC. IUPAC guidelines you people know, so just follow the guidelines and write the names of the organic compounds, okay. Yeah, as the number of carbon atoms increasing, the number of chain isomers are also increases. For example, in this case, an alkane having 7 carbons and 16 hydrogens, we can arrange in 9 different arrangements. So, I will take only the expanded form and I will write the name of this arrangement of the 7 carbons, okay, right. So, when we arrange the 7 carbons in a straight chain, CH3, CH2, 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 1, 2, 3, 4, 5, 6th one and the 7th carbon, okay. So, I can name it as heptane. Heptane is the name of this compound, heptane, one isomer that is possible, okay. Now, Let me take the second one. In this case, what I have to do, I will take only the 6 carbons in a straight chain and I will take the other carbons as substituents. Okay. So, when we go for the 6 carbons as a straight chain and a parent chain and the other carbon, 1 carbon as a substituent, so we can arrange that in this fashion: CH3, CH, CH2, CH2, CH, 1, 2, 3, 4, 5, 6. Okay. So, we can arrange the 6 carbons in a straight chain followed by 1 carbon as the substitution. So, I am taking the carbon as substitution at second position. Okay. Now, since I am having the carbon at second position, so if you want to name this carbon chain, what you have to do? You have to select the continuous carbon chain. So, when we are selecting the continuous carbon chain having maximum number of carbon atoms and numbering the carbon chain, so we can number the carbon chain from left to right. Second position we have methyl, so we can write the name of this compound as 2-methyl. 2-methyl, at second position we have methyl, so 2-methyl hexane. Hexane is the parent name and one substituent is present at second position, so I am writing it as 2-methyl hexane. Right. Is there any possibility with the 6 carbon chain? One more substitution is possible. So, in that case, if I observe, so I can write it as CH3, CH2, CH, CH3, CH2, CH2, CH3. 1, 2, 3, 4, 5, 6 in a straight chain and 1 as substitution. So, if I go for numbering of this particular carbon chain, so I am going from left to right so that the substituted carbon gets the lowest possible number, and again I have to mention the position of the substituent, that is methyl at third position, and I have 6 carbons in a parent chain, so it is hexane, 3-methyl hexane. So, 2-methyl hexane, 3-methyl hexane are 2 chain isomers that are possible with a 6 carbon chain. Can we write one more? No, it is not possible. If you take here, numbering should be given from this side, so it become 1, 2, 3. So, the same thing this compound is going to obtain. If we are going to keep the methyl at this position, we get the 2-methyl hexane. So, of course, only 6 with a 6 carbon straight chain and 1 as substitution, only 2 arrangements are possible. Right. Looking at the next one, if I take 5 carbons in a straight chain and 2 carbons as substituents. So, if I take CH3, CH, CH3, CH, CH3, CH2, CH3. So, I am taking 5 carbons in a straight chain and 2 carbons as substitution. At second position and third position I have taken the substitution. So, if I go for the numbering of this chain by selecting the longest continuous carbon chain having maximum number of carbon atoms, at second position I have substitution and third position I have substitution. So, I can write it as 2, 3 dimethyl, 2, 3 dimethyl pentane. So, just look at the number of carbon atoms. Pentane means 5, dimethyl 2, 2 plus 5, 7, 7 carbons are present in this one. So, it is a chain isomer of heptane. Okay. And if I am going to keep the methyl groups on other carbon atoms, in that case CH3, CH, CH3, CH2, CH, CH3, CH3. So, now if you observe, I have kept the 2 substituents at these positions. So, if I number the carbon chain by selecting the longest continuous carbon chain, at second position I have substitution, at fourth position I have substitution. So, I can write it as 2, 4 dimethyl. At second position we have methyl, at fourth position we have methyl. So, I am writing it as 2, 4 dimethyl. 2 methyls are present on second carbon as well as on fourth carbon, and 5 carbon chain it is pentane. So, 5 carbon chain means pentane means 5 carbon chain, 5 carbons plus 2 carbons, total 7 carbons are present. So, it is a chain isomer of heptane. Okay. And is there any possibility to have one more isomer from 5 carbon chain? Yes. So, if I go for the arrangement of carbon atoms, CH3, CH3, CH2, CH2, CH3, 1, 2, 3, 4, 5, 5 carbons in a straight chain and 2 substitutions are present, and the 2 substitutions are taken on the same carbon. So, now we can write it as 2,2 dimethyl pentane. So, 2,2 dimethyl pentane is possible. Okay. So, here when we are selecting the longest continuous carbon chain, so the substituted carbon should be given the lowest priority, and when we are numbering it, so at second carbon we are getting 2 substitutions. So, I am writing it as 2,2 dimethyl pentane is the name of the compound. So, is there any arrangement that is possible? Yes, we can also arrange the 2 substituents on the third carbon atom as well. So, let me remove or let me rub out the first one. Okay. I think you have noted down the isomer first one, 7 carbons in a straight chain. Okay. Right. Now, we can take the 7th isomer, 7th one, CH3, CH2, C, CH3, CH3, CH2, CH3. So, if you observe this molecule, we are arranging 5 carbons in a straight chain and 2 substituents taken at the third position at the middle carbon. So, when we number this compound in either direction, you are going to get the same numbering. So, at third position we have 2 methyls. So, I am writing it as 3, 3. Since the methyls are present, substituents are present on the third carbon atom. So, 3, 3 dimethyl, 3, 3 dimethyl pentane is the name. 3, 3 dimethyl pentane is the name of this compound. So, when we are arranging 5 carbon chain, 2 substituents can be taken at second and third position, second and fourth position, second and second position, third and third position. Is there any still one more possibility with 5 carbon chain? Yes, we have one more possibility. So, let me rub out the second one. I think I have noted down this one. So, when you arrange the 5 carbons in a straight chain followed by the 2 carbons, but of course, here I am taking the 2 carbons as a continuous chain like ethyl moiety. So, in that case, if I write the 8th isomer that is possible, CH3, CH2, CH, CH2, CH3. Okay. Now, I am taking the CH2, CH3. I am taking 2 carbons as a substitution now on a 5 carbon chain. So, this will be the longest continuous carbon chain. So, if I number the carbon chain, I will get 5 carbons in the side chain, but I am not keeping the 2 methyls side by side, aside, but I am connecting the 2 carbons connected with a single bond. So, I am taking it as a ethyl substituent. So, this is called as ethyl, ethane minus 1 hydrogen we get ethyl. So, ethyl is present, right. So, I am taking ethyl as a substituent. So, how to name this compound now? So, the compound can be named at third position on the parent chain. We have a substitution. What is that? Ethyl. So, I can write it as 3 ethyl. How many carbons we have in the chain? 5 carbons. So, it is pentane. So, how many different isomers are possible now? So, if you observe, we can clearly see that with the 4 carbon chain only, we can get around 1, 2, 3, 4, 5 isomers are possible. One more isomer is also possible in this molecule having a 7 number of carbon atoms. Okay. So, if I arrange the 4 carbons in a straight chain and then taking the other carbons as a substituents. So, only one possibility we can clearly see, CH3, CH3, CH, CH3, CH3. So, I am taking 4 carbons as a continuous carbon chain and 3 carbons as substituents. So, we can write it as 1, 2, 3, 4. Okay. So, at second position we have 2 substituents, at third position we have 1 substitution. So, I can write it as 2, 2, 3. 3 similar substituents are present. So, I am writing it as trimethyl, trimethyl butane. Trimethyl butane is the name of the compound. It is 2 comma 2 comma 3 trimethyl butane is one more isomer that is possible. So, 9th isomer we can write for this molecule. So, student, I think you have got an idea how to write the different chain isomer that are possible for the molecule. So, with a new topic we are going to see you in the next class, and till then have a nice time. Thank you.